Right, we are about to expose the absolute biggest hidden traps in the IGCSE computer science exam. Today, we aren't just going to rattle off boring textbook definitions, no way. We're going to look at the exact places where students unknowingly bleed marks, and we're going to completely transform how you approach these complex algorithms and systems.
Take a look at this classic trap right here, 10, 11, 10 in binary. What is that in our standard denary numbering system? Believe it or not, 9 out of 10 students actually get this exact binary conversion wrong under exam pressure. They rush it, they misalign the columns, and it quietly costs them an incredibly easy grade. Let me show you exactly where that error creeps in before you make it on exam day, because honestly, once you see the mistake, doing it the correct way becomes almost impossible to forget.
Okay, let's dive into this. Section 1. Mastering Binary and Denary.
You know, this whole architecture didn't just appear overnight. Way back in 1679, Gottfried Leibniz mapped out the foundational idea of binary. Later on, the brilliant Ada Lovelace realized how these super simple numbers could actually be used in digital processing. They essentially figured out that to make a machine process logical operations, you needed a system based entirely on precise numerical values, driven by really simple states.
And that brings us to the absolute core difference at the micro level. A bit, which is just short for binary digit, is simply a single 1 or 0. Think of it like a microscopic on or off switch mechanism. The computer reads a 1 as on, like there's an electrical charge, and a 0 is off, or no charge. But a single switch can't really do much on its own, right? That's where the byte comes in. A byte scales up that power by grouping exactly 8 bits together. This 8-bit group is the primary unit we use to measure computer memory size and the internal capacity of CPU registers.
So how do we actually conquer that conversion trap we talked about? Well, it's a simple logical sequence. First, draw out your denary columns from left to right, doubling the value as you move left. 1, 2, 4, 8, 16, 32, 64, and 128. Second, you place your binary digits directly below those columns. Finally, you just add up the denary values wherever there is a binary 1. That one basically acts as a trigger. It turns that column's value on. If you just follow these steps and always line up your columns starting from the right-hand side, you will literally never fall for the misalignment trap again.
Moving right along, Section 2, Binary Addition with Carries.
And this brilliantly illustrates the mechanics behind it all. An 8-bit register interacts directly with logic gates. When we add binary numbers together, we're essentially simulating the hardware, combining electric charges. The beauty of this system is its sheer mechanical simplicity, but you absolutely have to follow the strict laws of binary addition.
Those laws really just come down to 4 golden rules. The first 2 are pretty obvious, right? 0 plus 0 is 0, and 0 plus 1 is 1. But pay very close attention to the 3rd and 4th rules. Because the number 2 literally does not exist in the binary system, 1 plus 1 equals 10 in binary. So you write down the 0, and you carry the 1 to the next column. If you end up adding 3 ones together, the value is 11 in binary. So you write down the 1 and again carry a 1.
Now, massive examiner red pen warning here, guys. Keep this in mind whenever you see command words in the exam like calculate or show. You must start from the right side and write down every single carry and overflow bit. Why? Because even if you make a silly addition mistake and your final number is wrong, documenting your carry bits proves to the examiner that you understand the mechanism. That secures you crucial method marks that so many other students just leave completely on the table.
All right, let's shift gears. Section 3, Understanding Network Servers.
When computers share data, the whole system operates on a very specific 3-stage rhythm known as the client-server cycle. It starts with the client request, where your machine sends a message basically asking for a resource. Stage 2 is server processing, where the powerful central machine receives that request, retrieves the data, and performs the actual work. Finally, Stage 3 is the response, where the reply is sent back, officially completing the digital transaction.
Now, what's really interesting here is the sheer difference in role and power between the components. The server is the absolute powerhouse sitting in the center. It's the dedicated provider of resources. Surrounding it are the client nodes. These are the individual computers or devices that rely on the server to access shared files, processing power, or even internet routing. The network simply wouldn't function without this central authority managing all the traffic and workload.
When you're explaining this in an exam, remember this golden tip. One distinct point equals 1 mark.
Please don't waste your time repeating the same technical idea using slightly different words. The examiner is not going to give you extra credit for it. And most importantly, avoid generic answers. If the exam prompt talks about a school printer or a hospital database, use those exact scenario nouns in your answer to hit the top scoring bands.
Which leads us perfectly into Section 4, Internet Structure Exam Strategy.
To master this topic, we use what I call the technical reasoning roadmap. When you face a tough question about internet structure, you shouldn't just panic and start listing random vocabulary. First, you identify the exact requirements of the hardware or data structure. Next, you sequence your explanation logically, step 1, step 2, step 3. And finally, you anchor it directly back to the context the examiner provided. It's all about showing a super clear, logical train of thought.
Part of that reasoning is completely avoiding those classic textbook confusions that trap so many students. Let's clear these up right now. Validation and verification are absolutely not the same thing. Validation is an automated check to see if data is reasonable and actually follows the rules. Verification is checking if the data was entered correctly, usually by double entry or a physical visual check. Also, storage and memory, not interchangeable. Storage is your long-term, permanent filing cabinet, while memory is your active, volatile workspace. Mixing these up is a fatal error in the exam.
To ensure you never mix them up, you really need to rely on the method mark strategy. This strategy combines precise technical definitions with a visual rehearsal of the process. When you practice actually drawing out the diagrams of these networks and structures, it builds incredible scenario adaptability. You stop guessing what words to use, and you start visually recalling how the system actually fits together in real life.
And to lock in those full marks on long-form questions, I want you to run every single answer through this 4-prompt check. Ask yourself, did I state what it is? Did I explain the mechanism of how it actually works? Did I anchor it to exactly where it's used in the scenario? And did I provide a clear technical reason for why it is advantageous? If you hit all 4 of those prompts, you leave absolutely no room for the examiner to dock points for a vague answer.
Okay, home stretch, Section 5, final challenge and recap.
Let's do a quick interactive challenge. A student writes in their exam, the server validates the physical quality of the data entered. You have 10 seconds. Spot the fatal error. Have you got it? The trap is the word validates. Validation is an automated software rule check. For checking physical quality or ensuring data was entered completely identical to the source, the correct term is verifies. That one single wrong word drops the mark.
You guys have done fantastic work today, mastering these complex algorithmic mechanics and network structures. To keep building this momentum, make sure to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations.
But before we wrap up this explainer, I want to leave you with one final provocative thought. If data validation is really just a simple automated rule check, how does a network actually protect itself from malicious, intentional data corruption from an outside hacker? Think about that for a bit, and I'll see you in our next explainer as we crack open the fascinating world of cybersecurity.